recall that light is an electromagnetic wave. That is, it's an oscillating electric field combined with an oscillating magnetic field that propagates in a direction perpendicular to both. So we use this to talk about wave phenomenon and interference. But now we'll talk about a new aspect of this wave called polarization. Now, polarization refers to the orientation of the electric field with respect to other waves of light in that same beam. So think about it this way. Let's imagine a ray of light is going to your right on this screen. The electric field, let's imagine like a dolphin in the ocean moving up and down, diving up and down the waves. So there's a vertical polarization. That's the orientation of the electric field. And the magnetic field, which we don't care about now, of course, would be going horizontally. But the electric field doesn't have to go in this vertical direction. Maybe the electric field is moving like a snake side to side. Maybe it's at a 30-degree angle or a 75-degree angle. So if in a ray of light, in a beam of light, all of the light has the same orientation, all of the electric fields are oriented in the same way, we call that light polarized. If they aren't all in the same direction, we call that, or if the orientation is random, we call that either random polarization, which is probably more accurate, or the popular term is unpolarized. So what am I saying? So let's use this little part of the board here. Imagine a beam of light coming out towards you now. So the electric field could be vertically oriented, up and down. It could be horizontally oriented, or any infinite possible combinations of angles. Right? I could keep on drawing and keep on drawing and keep on drawing. This is randomly polarized. Or unpolarized light. Instead of drawing it like this, what's often done is it's given, you can see there are two components. They're breaking it down into an x and y axis. So this is equivalent to drawing it like this. Basically saying that there are components in the vertical direction, there are components in the horizontal direction. This is still unpolarized or randomly polarized light. We can put this light through what's called a polarizing filter. And a little picture will pop up here showing that from your book. So one analogy that I like to use is a rope through a narrow wooden fence. So imagine a fence with a lot of narrow slats, and of course you have the empty openings between each slat. What happens to be exactly the width of the rope. So you could take that rope and swing it up and down. Those waves would pass through the slat because the rope can move up and down through the opening. But if I took that same rope and moved it side to side, those waves could not pass through because the rope can't move side to side at the opening. So it only lets in waves of certain orientations. If I go at some other angle up and down, some of that wave will go through, but not all of it. So this is the idea of a polarizing filter. Again, the picture shown. If you have light in the orientation of the polarizing filter, that light will pass through unhindered. If the polarizing filter is perpendicular to the axis of polarization of light, which again is defined by the electric field orientation, then none of the light will go through. If it is somewhere in the middle where the angles aren't quite right, some component of the light will go through. Well, how do we figure out how much light goes through a polarizing filter? Well, the simplest way to start looking at this is unpolarized light. So when you have randomly polarized light or unpolarized light going through a polarizing filter, half of the light gets through, right? The half of the light that has the orientation in the direction of the filter. So I put this through a vertical filter, the vertical component will go through and the horizontal component won't. If I put it through a horizontal filter, the horizontal component will go through, the vertical component won't. If I put it through a 45-degree angle, the vertical component in the orientation of that angle goes through. The horizontal component in the orientation of that angle goes through. Half the light goes through in all cases. So the equation is very straightforward. The intensity of polarized light when you start off with unpolarized light is just 1/2. So by using a polarizing filter on unpolarized light, you cut the intensity by 1/2. And this is how polarizing sunglasses work. Polarizing sunglasses are glasses with a polarizing filter in front of them The sun's light is largely unpolarized. So just by putting on the glasses, you cut the light intensity in half. They have added features, which we'll talk about in just a bit with reflection, but polarizing sunglasses drop the light by 1/2. Now, if you have polarized light and you put it through a polarizing filter, what happens? So no longer talking about unpolarized light, but polarized light, light that has a specific angle, vertical, horizontal, or other, and you set it to a polarizing filter, what happens? It depends upon the orientation between the filter and the polarized light. Hopefully that makes sense, right? If I send a vertically polarized light through a vertical filter, they'll pass right through without any problem at all. If I send vertically polarized light through a horizontal filter, none of it will get through because there is no component of the wave that's waving horizontally, so none of it gets through. But what if it's some other angle? Well, it depends on the angle theta, where theta is the difference between the orientation of the polarized light and the filter. So if they're lined up, the angle is 0. If the angle is 0, cosine of 0 is 1. Square that, that's still 1. So the intensity is equal to the original intensity of the polarizing light. So all the light gets through, is what it says. I is equal to I naught. I naught is the initial light. I is the light on the other side of the filter. All of the light gets through. If you have a horizontally polarized filter, right, to vertical polarized light, that orientation is 90 degrees. Cosine of 90 degrees is 0. None of the light gets through. No intensity on the other side of the filter. What if it's at a 45-degree orientation, where it's a vertical 90 or 0, it's half? Well, plug in 45 degrees, cosine of 45 degrees, square it. That will tell you how much light goes through. So there are two equations here. One, the top one, is just from going from unpolarized light to polarized light. The intensity is cut by 1/2. The bottom equation deals with polarizing light going through a polarizing filter. So you can see how it depends on the orientation. Let's talk about what happens with polarized light and reflection. When looking at scattered light or reflected light, the process by which the light is scattered or reflected off of an object can change that light's polarization. So we call this Brewster's law. Brewster's law tells us the ideal angle that creates total polarization for reflected light. So tangent of Brewster's angle, theta sub b, is the angle at which light will become completely polarized. There's a little figure down here below from your book that will show the drawing better than I can do on the board of how light becomes horizontally polarized, reflected off of a surface. Now, the light usually, it's not completely polarized except at Brewster's angle. It just has more horizontal polarization than vertical polarization. If you've ever been fishing and you see the light reflecting off the lake or ocean or river, then you know that polarized sunglasses really do help cut down on the reflected light that you get from the water. And in fact, in some cases, depending on the angle at which the light reflects off the water, you can completely eliminate the reflected light using polarized sunglasses. So if we want to know what Brewster's angle is, it depends on the relative index of refraction between the two media. Again, if you're fishing, N1 is air, right? N2 is water. So you can calculate at what angle the incident light will be completely polarized depending on the mediums that you're dealing with. So you'll get a different answer if it's air and glass or air and diamond or water and diamond or whatever. Again, Brewster's angle here is the angle at which light is completely polarized. If you're not exactly at Brewster's angle, the light is just mostly polarized or it favors one direction versus the other. So since light is horizontally polarized after it's reflected, using vertical slits in your polarization filters on your lenses stops that horizontal light from coming through. So at Brewster's angle, all the light is stopped. Near Brewster's angle, the little bit that has vertical polarization does get through. You will see some reflected light. So polarized sunglasses don't work to stop all reflected light, but they do help cut it down. So polarized lenses have two major uses. One is it cuts unpolarized light and makes it polarized, so you drop all of the intensity of light by a factor of 1/2. And then reflected light, which is more horizontally polarized than vertical polarization, also has the advantage of cutting down a lot of reflected light. If you've ever been to a 3D movie, a modern 3D movie, you've used polarized glasses. In a modern 3D movie, two images are shown on a very special screen. Both are polarized at 90 degrees to one another. Then you put on the 3D glasses that have polarizing filters that are also 90 degrees to one another. So the left eye only sees the image the left eye is supposed to see, because the right image, which has a 90-degree polarization difference, doesn't get into the left eye. The right eye sees what the right eye sees because, again, only that image gets to the right eye. Now, if you tilt your head one way or the other, you can screw that up. Really fancy 3D movie theaters use what's called circular polarization, which your book doesn't get into. That's the electric field either spinning clockwise or counterclockwise. That's a better way of doing it, but it's also more complex, so we're not really going to talk about it in your textbook or in lecture. The polarization is actually very useful. All of you use it today. If you have what's called an LCD TV or screen, LCD means liquid crystal display. So an LCD TV has a white, basically, screen in front of a bunch of little polarizing filters that allow different colors through. So the electronics can very quickly turn on or off those polarizing filters, either allowing light through or blocking it. Ideally blocking all of the light, but it doesn't work quite that way. So the little red, green, and blue pixels on your TV screen at home are actually little LCD, little liquid crystal display electronics that either turn on or off a polarizing filter, either make it same orientation or 90-degree orientation, blocking light or allowing light through depending on what color that pixel needs to be at that time. Is it a night scene where it's dark? Well, then no light should be going through that pixel. Is it a bright scene during the day? Then you want light going through that pixel. And how quickly that can orient allows you to measure the speed of your TV and how quickly you can have images show up on your television. Many of you might have noticed if you look at a black screen on your television, it's still brighter than when the TV is off, because just a black screen on the TV, you still have the light behind the LCD screen producing light. A little bit of that light leaks through, which means that plasma TVs, for instance, have blacker blacks, because plasma TVs actually excite the pixels when they're needed, rather than just allowing light to transition through the pixel from a bright background. So plasma TVs can also burn in. So there are different pros and cons of each type of TV. I think LCD TVs are becoming the more popular choice. Less energy and also lighter. So this is the final discussion on polarization. This is actually concludes this section in this lecture about classical physics. And we'll start looking at modern physics with the next set of lessons.